The Sleepy Astronomer, a deep dive into cosmic mysteries. Welcome, fellow stargazers and cosmic dreamers, to another tranquil journey with the Sleepy Astronomer. Before we drift off into the cosmic expanse, I'm curious, where are you watching from tonight? Let me know in the comments below. Prepare to settle into your favorite cozy spot, and let your mind gently expand as we unravel the mysteries that shape our universe. From the subtle dance of disorder to the deepest theories attempting to unify all of existence. We'll explore the curious nature of entropy, the puzzling arrow of time, the hidden language of information. Many people think of entropy simply as disorder, and while that's a part of it, it's a much richer and more encompassing concept, one that speaks to the very statistical nature of reality. This statistical preference for evenly distributed, spread out states is the essence of entropy. It's why sugar dissolves in water, why heat flows from a warm object to a cold one, and why ice melts. These processes move from a state of lower entropy to a state of higher entropy, simply because there are far more probable arrangements for the energy and matter to occupy. This inherent tendency is enshrined in the second law of thermodynamics, which states that in an isolated system, entropy will always increase or, at best, remain constant. Why does time, for us, only ever seem to move forward? There's the thermodynamic arrow, which is the increase of entropy itself, the reason why systems naturally evolve from ordered to more disordered states. The universe started in a very low entropy state, the Big Bang, an incredibly ordered and dense beginning. From that moment, it has been expanding and evolving, steadily increasing its entropy, creating the very directionality of time that we perceive. At its heart, information theory, as pioneered by Claude Shannon, defines information as a reduction in uncertainty. A text filled with random letters has high information entropy because each letter choice is highly unpredictable, requiring more bits to encode. Consider Landauer's principle, which states that any logically irreversible manipulation of information, such as erasing a bit of data from a computer memory, must dissipate a minimum amount of energy as heat into the environment. The black hole information paradox is one of the most hotly debated topics in theoretical physics. It asks what happens to the information that falls into a black hole. If black holes eventually evaporate through Hawking radiation, does the information contained within them simply vanish, violating a fundamental principle of quantum mechanics that states information can never be truly destroyed? Or is the information somehow encoded in the faint radiation that escapes? This paradox pushes the boundaries of our understanding, hinting at deep connections between gravity, quantum mechanics, and the very nature of information itself, suggesting that information might be a fundamental property of the universe, just like energy and matter. This principle fundamentally links information to thermodynamics and energy, suggesting that information isn't just an abstract concept, but has a tangible, physical reality. It implies that information is not free. It costs energy to process and to erase. This concept has profound implications for understanding the limits of computation and the energy efficiency of future technologies. A coherent sentence, with its rules of grammar and common words, has lower information entropy because many parts are predictable, making it easier to compress. This universality of information theory extends far beyond human-made systems like telecommunications, data compression, and the Internet. It fundamentally applies to biological systems, like the genetic information encoded in DNA, which carries the blueprints for life. The sequence of nucleotides in a DNA strand represents an incredible amount of stored information, passed down through generations, guiding the complex processes of life. Imagine you're trying to guess the outcome of a fair coin flip. There's significant uncertainty, so when you learn the result, you gain a lot of information. But if you're trying to guess the outcome of a two-headed coin, there's no uncertainty, and thus no information gained when it lands. This concept, often quantified in bits, which are the basic units of information, helps us understand everything from how our computers work to how nature itself processes data. If the universe were to start contracting in a big crunch, the cosmological arrow might reverse, but even then, local entropy would likely continue to increase. The alignment of these arrows suggests a deep, fundamental connection. It's not just that things get messy, it's that the universe is evolving from a highly specific, ordered initial state towards a more general, disordered equilibrium, and this unfolding process is what we experience as the passage of time. It is a subtle yet powerful insight into why we exist in a universe where the past is fixed and the future is always unfolding. The past is a realm of lower entropy, while the future is where entropy continues to climb, guiding all events. Then there's the psychological arrow, our inherent experience of remembering the past, but not the future. This is likely tied to how our brains process and record information. Memory itself is a process of creating ordered neural pathways that reflect past events, and this process happens within an entropy-increasing universe. We build up memories because events unfold in a specific, irreversible sequence. Why do we remember yesterday, but not tomorrow? Why can't we unbreak a broken teacup or unscramble an egg? The laws of physics, at their most fundamental level, the equations themselves, are largely time-symmetric. They don't inherently care if time runs forward or backward. If you played a video of a ball bouncing, you couldn't tell if it was running forward or backward, based solely on the physics of the bounce. Yet, in our everyday experience, time is undeniably unidirectional. The answer, as we've begun to see, lies predominantly with entropy. The reason a teacup shatters, but never spontaneously reassembles, is because the shattered state has vastly higher entropy, far more ways for its pieces to be arranged than the single, unbroken state. The universe, guided by the second law, moves towards these higher entropy states, giving time its forward direction. It's a fundamental rule of the cosmos, quietly guiding everything from the cooling of your evening tea to the slow, inevitable expansion of the universe itself. Imagine a meticulously organized library where every book is in its precise place. For any given macroscopic state of a system, like a glass of water at a certain temperature, there are an enormous number of different, microscopic arrangements of the individual water molecules and their energies that can result in that same macroscopic state. These microscopic arrangements are called microstates. A state with higher entropy is simply a macroscopic state that corresponds to a vastly greater number of possible microstates. So, when ice melts, the water molecules in their liquid form have many more ways to arrange themselves and distribute their kinetic energy than they did in the rigid, crystalline structure of ice. This isn't about some inherent desire for messiness. It's a consequence of probability and the sheer numbers involved in statistical mechanics. Now, imagine a curious child let loose within it. Why can't we spontaneously unmix cream from coffee or reverse the aging process? Because reversing these processes would mean moving from a high entropy state to a much lower one, requiring an incredibly improbable, precisely coordinated arrangement of countless particles. While theoretically possible on a microscopic scale for tiny fluctuations, it's virtually impossible on macroscopic scales due to the overwhelming statistical odds. This constant increase in entropy also has profound implications for the ultimate fate of the universe, leading some cosmologists to hypothesize about the heat death of the universe, a distant future where all energy is evenly spread out and no work can be done, leading to a state of ultimate thermodynamic equilibrium. But don't worry, that's billions upon billions of years away, leaving us plenty of time to enjoy the cosmic dance. Over time, books are pulled from shelves, covers are scattered, and chaos seems to reign. This seems like disorder, right? But from a physicist's perspective, entropy is more about the number of ways a system can be arranged. A perfectly ordered library has only one specific arrangement. A disordered one, with books strewn about, has vastly more possible ways for the books to be scattered. The universe, in its grand dance, naturally tends towards states that have the highest number of possible configurations, the most ways for its components to be arranged. And the grand quest to reconcile the quantum world with the pull of gravity, venturing into the fascinating realms of dark matter and dark energy as well. Your insights truly light up our little corner of the universe. Tonight, we're not just observing the distant cosmos. We're truly immersing ourselves in the very fabric of reality. Entropy, the universe's gentle tendency toward spread. Our expedition begins with perhaps one of the most fundamental, yet frequently misconstrued, ideas in all of science. Entropy. Think of it this way. If you have a box filled with gas, there are countless more ways for those gas particles to be spread evenly throughout the box than for them to all spontaneously gather in one corner. Let's delve a little deeper into the microscopic perspective. Understanding entropy also helps us grasp the concept of irreversibility in nature. The arrow of time. Why time marches on, this profound concept of increasing entropy, leads us directly into one of the universe's most puzzling features, the arrow of time. There are different arrows of time that all point in the same direction, reinforcing this cosmic flow. We also have the cosmological arrow, which refers to the expansion of the universe. Information theory, the universe's hidden language now. Let's explore the intriguing landscape of information theory, a field that may seem abstract, but is deeply intertwined with physics and how we understand reality. A key aspect is information entropy, or Shannon entropy, which measures the unpredictability or randomness of information. But the connection between information and physics goes even deeper. Furthermore, information theory plays a crucial role in our understanding of exotic phenomena like black holes. Quantum mechanics and gravity. The grand unification quest. Finally, we arrive at one of the grandest challenges in modern physics, the quest to unify quantum mechanics and gravity. On one hand, we have quantum mechanics, the incredibly successful theory that describes the strange, but as the curvature of space-time, caused by the presence of mass and energy. Imagine placing a bowling ball on a stretched rubber sheet. It creates a dip. String theory proposes a radical departure from our current understanding of fundamental particles. It also predicts the existence of extraspatial dimensions beyond the three we perceive and the one of time. The energies required to probe these tiny strings are astronomically high, far beyond the capabilities of any current or foreseeable particle accelerator. So, direct experimental evidence is still elusive, and it faces challenges, including the existence of multiple possible string landscapes or solutions. These aren't just theoretical constructs. They represent profound observational puzzles that challenge our current understanding of the cosmos. The visible matter stars, gas, and dust simply wasn't enough to explain the observed rotation speeds. For a long time, cosmologists expected the expansion of the universe, which began with the Big Bang, to be slowing down due to the gravitational pull of all the matter within it. One leading hypothesis is that dark energy is a property of space itself, inherent in the vacuum of space, often referred to as the cosmological constant originally proposed by Einstein, but later discarded by him. As space expands, more space is created, and therefore, more dark energy comes into existence, continuously driving the acceleration. Another idea suggests it might be a new kind of dynamic energy field, sometimes called quintessence. Every new discovery opens up more questions, pushing the boundaries of human knowledge and reminding us of the endless mysteries waiting to be explored. So as you drift off into the cosmic expanse tonight, remember the elegance of entropy, the relentless march of time, the hidden messages in information, the profound quest to unify gravity with the quantum realm, and the silent, invisible influence of dark matter and dark energy. Dark energy currently constitutes about 68% of the total energy density of the universe, while dark matter accounts for about 27%. May your mind be filled with wonder and your dreams with the mysteries of the universe. If you found this extended journey soothing and enlightening, please consider giving this video a gentle cosmic thumbs up, subscribing to the channel for more serene science adventures, and sharing your thoughts and your own cosmic curiosities in the comments below. Until next time, keep looking up, keep dreaming big, and may your slumber be filled with stardust and the profound quiet of the cosmos. Good night, sleepy astronomers. Meaning all the ordinary matter we can see and interact with, including stars, planets, and ourselves, makes up only about 5%. These two dark components represent the vast majority of our universe, yet they remain largely unknown, challenging physicists to develop new theories that can incorporate these cosmic unknowns into a more complete picture of reality. Their existence pushes the boundaries of our cosmic understanding, reminding us how much more there is to discover about the universe we inhabit. However, observations of distant supernova in the late 1990s revealed something truly astonishing. The expansion of the universe isn't slowing down. It's actually accelerating. This discovery was a complete shock, implying that there's some mysterious force pushing space-time apart, counteracting gravity. This force has been dubbed dark energy. From the subtle statistical tendency towards entropy that defines the flow of time and the irreversibility of events, to the invisible language of information that underpins reality and the very nature of black holes, and then to the grand ambition of uniting all forces into a single elegant theory like string theory, and finally, grappling with the mysterious dark matter and dark energy that dominate our cosmos. Physics continuously invites us to look deeper, to question, and to marvel. These aren't just abstract ideas. They are the fundamental rules that shape everything around us, from the smallest subatomic particles to the largest galaxies. Unlike dark matter, which clumps together due to gravity, dark energy appears to be smoothly distributed throughout space, acting like a pervasive anti-gravitational pressure. Galaxies were spinning so fast that they should fly apart, much like a merry-go-round spinning so quickly that the riders are flung off. Yet, they remain gravitationally bound. The only way to explain this is if there's a huge amount of unseen, non-luminous matter exerting a gravitational pull. We call this dark matter. It doesn't emit, absorb, or reflect light, so we can't see it directly. We only infer its existence through its gravitational effects on visible matter. Evidence for dark matter also comes from galaxy clusters, where the gravitational lensing of light from background galaxies reveals far more mass than can be accounted for by visible matter alone. Cosmological simulations of structure formation also require dark matter to explain how galaxies and clusters formed from the early universe as almost uniform state. While its exact nature remains one of the biggest mysteries in physics, leading candidates include exotic particles that interact very weakly with normal matter, such as WIMPs. Experiments deep underground and in space are actively searching for direct evidence of these elusive particles. Nevertheless, it continues to inspire physicists, offering profound conceptual insights into the nature of space, time, matter, and the very structure of our cosmos, guiding us towards a deeper understanding of the universe's ultimate secrets. These extra dimensions are thought to be curled up so tightly at incredibly tiny scales that we don't experience them directly. Think of a garden hose from afar. It looks one-dimensional, but up close, you see it has a second curled-up dimension. Similarly, these extra dimensions could be hidden to us, influencing physics at the most fundamental levels. Instead of point-like particles, it suggests that the most basic constituents of the universe are tiny, one-dimensional vibrating strings, unimaginably small, far smaller than an atom. Just as the different vibrations of a violin string produce different musical notes, the different vibrational patterns of these fundamental strings are what give rise to all the various particles we observe. Electrons, quarks, photons, and crucially, the graviton, the hypothetical particle that carries the gravitational force. In string theory, gravity isn't separate. It's an inherent part of the string's vibrational spectrum. Now roll a marble nearby, and it will curve towards the bowling ball. That's essentially how general relativity explains gravity. Massive objects warp the fabric of space-time around them, and other objects simply follow these curves. This theory beautifully explains the motion of planets, the bending of light around massive objects, and the large-scale structure and expansion of the universe. It's a theory of the very big, deterministic, and geometrically elegant, and probabilistic world of the very small, atoms, electrons, photons, and all the fundamental particles that make up reality. In this realm, particles don't have definite positions or momenta until measured. They can exist in multiple states at once, and they can be mysteriously linked across vast distances. It's the world of the uncertainty principle, where there are fundamental limits to how precisely we can know certain pairs of properties about a particle. It's a universe governed by probabilities and wave functions, where reality seems fluid and dependent on observation. On the other hand, we have Albert Einstein's magnificent theory of general relativity, which describes gravity not as a force. The problem arises when we try to apply these two theories simultaneously to extreme environments where both quantum effects and strong gravity are at play, such as inside a black hole at the very beginning of the universe during the Big Bang, or at the incredibly tiny Planck scale. They use completely different mathematical languages and make conflicting predictions. Quantum mechanics struggles to describe gravity, and general relativity doesn't incorporate quantum principles. This fundamental incompatibility is why physicists are desperately seeking a theory of quantum gravity, a single, unified framework that can describe all forces and particles, from the smallest to the largest scales. This is where speculative but compelling ideas like string theory emerge as leading contenders. Remarkably, string theory naturally incorporates gravity within its framework, which is why it's considered a leading candidate for a theory of everything, a single unified description of all the fundamental forces of nature. While string theory offers a mathematically elegant and consistent picture of reality, it remains a theoretical framework. The cosmic enigma, dark matter and dark energy. As our journey deepens into the mysteries of the universe, we encounter two of its most enigmatic components, dark matter and dark energy. First, let's talk about dark matter. When astronomers looked at how galaxies rotate, they found something puzzling. Then there's dark energy, an even more perplexing enigma. Its nature is even less understood than dark matter. Conclusion: the unending cosmic dream. As our extended, tranquil journey through these profound concepts comes to a gentle close, let us take a moment to appreciate the sheer wonder of a universe governed by such intricate and beautiful principles. The universe is a vast, interconnected tapestry of wonders, and understanding its deepest secrets is a journey that continues to unfold, one concept at a time. Thank you for joining the Sleepy Astronomer on this deep dive into cosmic exploration.